If you have ever sat in front of a game and felt genuinely moved by how it looked, this video is for you. And if you have ever wondered why your expensive machine still stutters, still tears, still disappoints you at 4000 pixels of resolution, this video is especially for you. Stay until the end. What you learn here will change how you see every game you play from this moment forward. Let us begin at the beginning. With light. For centuries, painters and philosophers alike have understood that light is not simply illumination. It is the medium through which reality is interpreted. When Leonardo da Vinci painted the soft shadows beneath a human chin, he was not painting darkness. He was painting the absence of light and the gradual, gentle transition between the two. That subtlety, that softness, is what the human eye recognizes as real. For decades, video games could not replicate this. Shadows were hard-edged and artificial. Reflections were pre-baked illusions frozen in place, unable to respond to a moving world. Light sources behaved like performers hitting their marks on a stage, convincing enough from a distance, but hollow up close. The game world was, in a fundamental sense, lying to you. Ray tracing changed that conversation entirely. The technology works by simulating the actual physical behavior of light. In the real world, when a photon of light leaves a source, it travels outward, strikes a surface, and either bounces, bends, or is absorbed, depending on what that surface is made of. A mirror sends it back in a clean angle, water bends it. Rough stone scatters it in 1,000 directions. Ray tracing calculates all of this mathematically, tracing each ray of light as it interacts with the virtual world, moment by moment, frame by frame. The result is something genuinely startling the first time you see it. In a game like Cyberpunk 2077 with full ray tracing enabled, the neon lights of Night City reflect on wet pavement with a physical accuracy that feels less like a video game and more like a cinematic render. The soft glow of a lamp bleeds realistically around the edge of a wall. A mirror in a bathroom shows you your character's face. Not a flattering, faked approximation, but a genuine real-time reflection. These are not tricks. They are simulations. Ray tracing does not make you a better player. It does not sharpen your aim or improve your reaction time. What it does is something more intimate. It deepens immersion. It makes you forget for a moment that you are sitting in a chair looking at a screen. And that forgetting, fragile and brief as it is precisely what game designers have always been chasing. But beauty has a cost. And this is where the story becomes more complicated. Ray tracing is computationally brutal. The number of calculations required to trace even a fraction of the light rays in a single frame is staggering. Even the most powerful graphics cards in the world, the kind that cost more than a used car, struggle to run ray tracing at high resolutions while maintaining smooth, playable frame rates. This created a dilemma. The technology existed to make games look real, but the hardware could not sustain it without compromise. Nvidia's answer to this dilemma was not to make the hardware work harder, it was to make the hardware work smarter. In 2018, Nvidia introduced DLSS deep learning supersampling. The concept, when explained plainly, sounds almost like science fiction. Instead of rendering a game at the full resolution your monitor displays, DLSS renders it at a lower resolution, sometimes significantly lower, and then uses a trained artificial intelligence to reconstruct the missing detail and upscale the image to full resolution. The AI does not simply stretch pixels. It predicts what the image should look like, drawing on a vast library of high-resolution reference data it was trained on. The results, particularly in later versions of the technology, are remarkable. In many cases, DLSS at a high-quality setting produces an image that is sharper and cleaner than a natively rendered frame at the same resolution. This is not a paradox, it is the nature of AI prediction. The network has learned, through millions of examples, how fine detail should appear. It can extrapolate from limited information with an accuracy that brute force rendering sometimes cannot match. And the performance gains are substantial. A game that runs at 60 frames per second in native 4K resolution might run at 120 frames per second with DLSS enabled, essentially doubling the smoothness of motion. For players who run ray tracing alongside DLSS, the combination is particularly powerful. The two technologies were, in a sense, designed for each other. Ray tracing demands performance headroom. DLSS provides it. Together, they make it possible to have a game that looks visually accurate and runs smoothly, something that would have been impossible on consumer hardware just a few years prior. Not everyone, however, owns an Nvidia graphics card. And this is where a different kind of ingenuity entered the story. AMD, Nvidia's primary competitor in the graphics card market, developed their own upscaling solution called FSR Fidelity FX Super Resolution. Where DLSS relies on specialized AI hardware that is only present on Nvidia's graphics cards, FSR takes a fundamentally different approach. It uses a set of open-source spatial upscaling algorithms that run on any modern GPU, regardless of manufacturer. An AMD card from 2020, an older Nvidia card from 2017, even the graphics processors inside gaming consoles, all of them can run FSR. This was a philosophically significant choice. Nvidia built a technology that works brilliantly, but only for those who can afford the right hardware. AMD built a technology that works broadly, extending the lifespan of aging systems and giving budget-conscious players access to meaningful performance improvements. In a market where graphics cards routinely cost $500, $800, even over $1,000, that accessibility matters enormously. The trade-off is image quality. FSR, particularly in its earlier versions, does not match the sharpness and reconstruction accuracy of DLSS at equivalent settings. Fine details, hair, foliage, distant text can appear slightly softer. Motion can introduce more visible artifacts. But for a player running a 3-year-old graphics card who simply needs more frames to make a game playable, FSR is not a compromise. It is a lifeline. It is the technology that says, you do not have to buy new hardware today. What you have is still enough. And then there is a third layer to this story, a technology that takes the concept of artificial intelligence and pushes it in a direction that initially sounds either brilliant or deeply questionable, depending on your perspective. Frame generation inserts entirely artificial frames between the real frames your graphics card renders. If your GPU produces 60 real frames per second, frame generation can present the visual appearance of 120 frames per second by generating 60 additional frames using AI prediction. The motion you see on screen becomes silkier, more fluid, more cinematic. In a game with beautiful, sweeping camera movements, a racing game, an open-world adventure, a cinematic action title, this can feel genuinely transformative. But there is a catch that becomes immediately apparent the moment you use frame generation in a competitive game. The artificial frames are generated after the fact. They are predictions about what motion should look like, not responses to your actual inputs. This introduces latency, a small but measurable delay between what your hands tell the game to do and what your eyes see on screen. In a single-player game where you are exploring a landscape, this delay is imperceptible and irrelevant. In a competitive multiplayer game where the margin between winning and losing a firefight is measured in milliseconds, it becomes a liability. Frame generation is, in this sense, a technology with a very specific audience. It rewards patience and observation. It punishes reflex. Every one of these technologies, ray tracing, upscaling, frame generation, ultimately runs up against the same physical constraint. Memory, VRAM, or video random access memory, is the dedicated memory built into a graphics card. It stores everything the GPU needs immediate access to: textures, shaders, models, lighting data. Think of it like a chef's workbench. The chef may have a massive kitchen full of ingredients and equipment, but what matters in the heat of service is what is within arm's reach. When the workbench fills up, service slows down. Things get dropped. At 1920 by 1080 resolution, what most players still game at, VRAM demands are manageable. Modern games typically require somewhere between 6 and 8 gigabytes. But at 2560 by 1440 resolution, or at 4K, the demands multiply rapidly. High-resolution texture packs can consume 12 to 16 gigabytes on their own. When a game runs out of VRAM, the consequences are visible and unpleasant. Textures that refuse to load properly. Sudden drops in frame rate that feel like the game is choking, persistent stuttering that no amount of settings adjustment will resolve. This is why the VRAM specifications of a graphics card matter so much in 2025. Buying a card with 8 gigabytes of VRAM to play 4K games is not a budget decision. It is a guaranteed source of frustration. The technology exists to play beautiful games. The memory must exist to support it. There's an entire family of technologies that most players adjust without truly understanding what they do. Anti-aliasing is perhaps the most common of these. The fundamental problem anti-aliasing addresses is called aliasing, the staircase effect that appears on diagonal edges in digital images. Because screens are made of square pixels arranged in a grid, any line that does not run perfectly horizontal or perfectly vertical will appear jagged. The human eye, trained by a lifetime of looking at a world full of smooth, continuous curves, finds this jarring. Anti-aliasing smooths these edges by blending adjacent pixels, creating the visual impression of continuity. Different methods achieve this with different levels of success and at different costs to performance. Older techniques like MSAA multi-sample anti-aliasing were effective but expensive. More modern temporal approaches, which gather information across multiple frames to smooth edges over time, are generally more efficient but can introduce a slight blurring of motion. DLSS, in fact, incorporates its own form of temporal anti-aliasing as part of its reconstruction process, which is one reason DLSS images can appear so clean even at aggressive upscaling ratios. Anisotropic filtering is another setting that most players leave untouched, often because it sounds intimidating. The concept, however, is simple. Textures in a three-dimensional game must be displayed at many different angles and distances simultaneously. A stone floor that looks crisp directly beneath your character's feet will, without anisotropic filtering, look blurry and undefined as it stretches toward the horizon. Anisotropic filtering corrects this by applying different levels of texture detail depending on the viewing angle. On modern hardware, enabling anisotropic filtering at its highest setting, 16 times, has almost no measurable performance cost. The GPU hardware dedicated to this task is so efficient that the impact on frame rate is negligible. And yet the visual improvement, particularly in open-world games with expansive vistas, is immediately visible to any observant eye. This is one of those settings where the advice is unambiguous. Enable it, set it to the maximum, and never think about it again. Even after the image is rendered correctly, there remains the question of how it arrives on your monitor. And this is where two technologies, one old, two modern, shape your experience in ways that go beyond raw frame rates. V-Sync, which stands for vertical synchronization, was the original solution to screen tearing, the visual artifact that occurs when your GPU delivers frames at a rate that does not align with your monitor's ZES refresh rate. When this misalignment happens, the monitor displays parts of two different frames simultaneously, creating a visible horizontal split in the image. V-Sync prevents this by locking the GPU's frame output to the monitor's refresh rate. If your monitor runs at 60 Hz, V-Sync ensures the GPU delivers exactly 60 frames per second, no more, no less. The limitation of V-Sync is that this lock is rigid. If the GPU cannot maintain 60 frames per second, if a complex scene drops performance to 55 frames, V-Sync forces the game down to 30 frames to maintain synchronization. This sudden halving of smoothness is jarring and counterproductive. V-Sync also introduces a small degree of input lag, because frames must wait to be delivered in sync with the monitor's cycle. G-Sync and FreeSync solved this problem by inverting the relationship. Instead of locking the GPU to the monitor, these technologies make the monitor respond to the GPU. The monitor refreshes as often as the GPU delivers a new frame, whether that is 42 frames per second in a demanding scene or 118 in a simpler one. The result is a fluid, tear-free experience across a wide range of frame rates, without the rigidity or the latency penalty of V-Sync. G-Sync is Nvidia's proprietary implementation, requiring specific hardware in both the graphics card and the monitor. FreeSync is AMD's open standard, supported by a far wider range of monitors at a lower price point. Nvidia graphics cards can also function with FreeSync monitors, though with some limitations. Neither technology makes games run faster. What they do is make whatever speed your games run at feel better, smoother, more natural, more like the experience of looking through a window than staring at a screen. Beneath all of these visual systems, there is an even more fundamental layer that most players never consider at all. Shaders. Shaders are small programs that run on the GPU and control how every surface in a game is rendered. They determine how a material reflects light, how shadows fall across geometry, how water moves and refracts, how fire glows and disperses. Without shaders, a three-dimensional scene is simply geometry, shapes without substance. Shaders are what give those shapes the appearance of material reality. More advanced shaders produce more realistic results, but they also demand more from the GPU. This trade-off is visible in the settings of virtually every modern game. The difference between low and ultra shader quality settings is often the difference between a game that runs at 200 frames per second and one that runs at 60. Shader compilation is a related issue that has frustrated players significantly in recent years. Before shaders can run on the GPU, they must be compiled, translated from the programming language in which they were written into a format the GPU hardware can execute. Many modern games perform this compilation either during installation or during an initial loading phase. But some games handle it poorly, deferring compilation until shaders are first encountered during gameplay. The result is the stuttering that many players have experienced even on high-end hardware, a brief, jarring hitch the first time a certain effect appears on screen. This is not a hardware failure. It is a compilation delay. Understanding this distinction can save considerable frustration. Finally, there is a technology that matters enormously to a specific audience, but is often overlooked in broader conversations about graphics and VRAM. For players who record their gameplay or stream it live to an audience, performance is always a tension between two competing demands. Running the game at its best possible quality requires the full resources of the GPU. Encoding a high-quality video stream requires significant computational power from the CPU. On systems without dedicated encoding hardware, these two demands compete directly, and something must give. Nvidia's hardware encoder, built directly into their graphics cards, eliminates this competition. It handles video encoding on a dedicated chip that exists separately from the cores responsible for rendering the game. A player streaming at 1080 pixels, 60 frames per second, with a high-quality bitrate, will see almost no impact on their in-game performance. The game and the stream run in parallel, each handled by specialized hardware designed for exactly that task. For content creators, this is not a minor convenience. It is the difference between running a stream at full quality and running it at a compromised setting to avoid destroying game performance. In a landscape where streaming and content creation have become major parts of gaming culture, NVENC is one of the most practical technologies on this entire list. What does all of this mean when taken together? Here's the lesson that emerges from this survey of invisible technologies. The quality of your experience, not just in games but in any complex system, is rarely determined by one thing alone. It is determined by how well many things work together. Ray tracing needs DLSS to be sustainable. DLSS needs sufficient VRAM to function correctly. Frame generation needs the right context to be valuable rather than harmful. G-Sync and FreeSync make your frame rates feel better, but only if your frame rates are already reasonable. Every element in this chain depends on every other element. This is true beyond gaming. Any system, a team, a workflow, a relationship, performs not at the level of its strongest component, but at the level of how well its components are aligned. Understanding each piece individually is useful. Understanding how they interact is wisdom. Ask yourself honestly, in your own setup, your own life, your own work, which components are you neglecting? Which settings have you left at their defaults because they seem too technical, too abstract, too unlikely to matter? More often than not, those overlooked details are precisely where the meaningful improvements are hiding. The next time you sit down to play a game and it looks extraordinary, when the light catches the edge of a surface in a way that makes you pause, when the shadows fall with a softness that feels almost painterly, you will know what is happening behind that image. You will know the name of the engine. You will understand the architecture of that beauty. And perhaps more importantly, you will understand that nothing of genuine quality is ever the result of one thing working perfectly. It is always many things working together, each one supporting the others, each one dependent on the whole. Take care of your setup, understand your tools, and build your foundation, in games and in life, with the same attention to invisible detail that the best technology demands. If this video opened your eyes to something you had never considered before, share it with someone who spends time in front of a screen. Leave a question in the comments about your setup, your settings, your experience. Your questions shape the videos that come next. And if you have not subscribed yet, this is the moment. Stay with this channel. There is much more to explore, and the next video may be exactly what you have been looking for.